Hi there, my name is Caleb Nell, and today I'm going to be showing you my multi-threaded ray tracer for the Graphics and Computational Programming module at Bournemouth University. And we're going to be discussing the theory, the design, I'm going to be showing you a demo of the program, an analysis of the program, and finally the evaluation. In order to understand what ray tracing is, we need to first understand how we see 3D objects. The original method is called rasterization. This works by shining the light onto the objects and reflecting that light back into the camera. In ray tracing, the light is shone onto the objects. However, when the camera renders the scene, rays will shoot from the camera's perspective and the pixels on the screen will be shaded in the exact color that is chosen in the scene. In order to draw the geometry, an overridden pure virtual Boolean function was created in the object class, which is called ray intersection. This has a ray object as a parameter. In this function, a ray will be cast onto any place on the screen. In the main program, this is set to every pixel in the viewport and is used to calculate whether the ray has hit any geometry. The distance from the ray is then calculated using a function called calculateDistance, which has a return type of a GLM 3D vector. This function implements the distance calculation found in Euclidean mathematics, which is expressed as the following. The parameters used for this distance calculation is the origin of the sphere, origin of the ray, and the direction of the ray. The scalar value of distance from the closest point on the line to the center of the sphere is then obtained from this equation. We can then compare it with the radius of the sphere. At this point we know there is a hit, and we need to work out the intersection point. If the function does not get this far, it will simply return false. The equation to find the actual intersection point is then implemented. Once the intersection is confirmed in this part of the function then returns true. All of the shading takes place in the shade pixel method inside of the sphere class. This method is similar to OpenGL shader programs in GLSL. First, the surface normal is needed between the intersection point and the center of the sphere. The position of the light is then set. The normalized light will then need to be obtained by doing a dot product between the light position and surface normal vectors. The function will then return the pixel light variable multiplied by the chosen light color in order to shade the geometry the correct color. The multi-threaded method allows the user to split the screen into portions by choosing an amount of threads. Each thread is responsible for rendering a division on the screen. Other shading methods include physically based rendering. There's also ray trace shadows. Finally, we have ray trace reflections. Now let's talk about the system design. The different classes are the object class, the sphere class, which inherits from the object class, and finally the actual ray tracing system, which includes the camera, the ray, and the ray tracer. The camera generates the ray for every pixel which is traced using the ray tracer. The multi-threaded part of the program is made up of two functions. One function to draw any part of the screen called drawScreenPartition, and one function to split up the screen into any amount of portions called splitScreen. Let's imagine that we have a screen with a game being played. The multi-threaded ray tracer will have the ability to draw a portion of the screen. Let's imagine that the limits given to the function is the entire screen. Then the screen is split up into portions, and each thread is responsible for rendering a specific part of that screen. Other multi-threaded method is called thread pooling. This uses a fixed number of a group of threads to execute tasks simultaneously. This is basically parallel programming. As you can see, there are 3 spheres in the foreground. There's also 1000 spheres in the background. This is because with just 3 spheres, my program did not show any significant benefit to the multi-threading. These are the performance results. The y-axis shows the amount of threads used for each test, and the x-axis shows the amount of time to render the scene. The scalability and percentage difference between each data point has inconsistent scaling. The average time gets smaller as the amount of threads increases, until it gets to about 16 threads, then it starts to go back up. It then drops again at 64 threads. This is most likely due to the amount of overhead of creating so many threads. Looking at the qualitative aspects of my implementation, there are many things to talk about. The lack of any realistic shadows or global illumination is obvious. The spheres, although being 3D objects, end up looking quite flat. They also have jagged edges and are not as rounded as I would have liked them to be. There's also been no real implementation of anti-aliasing. If I compare this scene with the other implementations, such as the Cornell Box has implemented diffuse materials on the walls and has added a glass sphere to demonstrate global illumination and reflections. And now finally, the evaluation. Speed of the program doesn't really improve from this method of multi-threaded rendering until the program becomes more complex. This is most likely due to the overhead of creating so many threads. This is where something like thread pooling would become extremely effective at helping reduce the computational time. The scalability is inconsistent as the thread count increased. This program seems to beg the question whether or not there are any benefits to getting the same quality image out of the program at a faster rate. So perhaps something like a time test would have been better. Work to time the program for about a minute and see what quality of the scene can be produced by each set of threads. Thank you very much for listening, and here are my references.